Last time on Penguin Physics, we learned about 4 fundamental forces, focusing primarily on the gravitational force and the electromagnetic force. We found that within the realm of the electromagnetic force was the electrostatic force, which was responsible for all of the contact forces we experience in our daily lives. The applied force, the general force between two objects, the normal force, the supporting force, the force of friction, the resistive force against motion, tension, the pulling force in strings, and the spring force, the restoring force in springs. We learned that any of these forces, when unbalanced, cause acceleration. Such is Newton's first law, and it governs the motion of all objects. It's such a simple yet nuanced statement. Let's clarify what Newton's first law is really telling us about motion. When analyzing the external forces acting on an object, we can determine those forces to either be balanced or unbalanced based on the net total force. If the net force on an object totals to 0, the forces on the object are said to be balanced. If the net force on the object totals to anything but 0, the forces on the object are said to be unbalanced. Balanced forces do not cause acceleration, and therefore the object will keep doing whatever it was already doing. If it was at rest, it'll stay at rest. If it was moving, it'll continue moving at constant velocity. It's unbalanced forces that cause an acceleration, and that acceleration is in the same direction as the net force. Now remember, force is a vector quantity. So when we talk about the net force, we are essentially talking about the resultant force. We can represent this with a capital letter, sigma, that represents a summation. Let's look at an example. A cup of coffee sits at rest on a table. What forces act on the cup? Well, the gravitational force of Earth is always pulling any object towards Earth. The cup doesn't fall through the table because the table responds and supports the cup through the normal force. Since the cup isn't in contact with any other object, there's no applied force. Since it isn't being pulled apart or stretched or compressed, it doesn't experience the tension or spring force. And finally, since it isn't moving or attempting to move, there's no friction between the cup and the table. Great, so we know this cup experiences 2 forces, the force of gravity and the normal force. The force of gravity always acts downward, and the normal force always acts perpendicular to the surface. But how do the size of these vectors compare? This is where Newton's first law comes in handy. Since this cup is at rest, we know that the net forces must equal 0. So when we draw our downward gravitational force vector and our upwards normal force vector, we draw them with equal lengths such that their total would equal 0. What we did here is we analyzed the forces acting on an object and used Newton's first law to represent those force vectors and their relative sizes. This force diagram is called a free body diagram, and it is one of the most useful tools that we physicists use. Let's try another example. You're pushing a can of tomato soup, causing the can to accelerate across a level surface. How might we visualize the forces acting on the can of soup in this situation? Let's start with which forces apply. Just as before, we can include the gravitational force of Earth on this can and the normal force from the table. You are applying a force when you push the can, and when that can is sliding across the table, we know that there's a frictional force that acts against the direction of motion. Excellent! Let's start diagramming. Like we discussed in our previous videos, horizontal and vertical motions are completely independent, which means horizontal and vertical forces must also be independent. So let's analyze them separately. The gravitational force points downward, the normal force upwards perpendicular to the surface. Vertically speaking, the can's motion is constant. This means the can's vertical acceleration is 0, and that indicates the vertical forces total to 0 as well. Mathematically, we can write this as the summation of vertical forces is, or equals, the force of gravity plus the normal force in the opposite direction, and this sum equals 0. Visually, we can draw these two vertical vectors with equal magnitudes in opposite directions. Horizontally speaking, we have the applied force from your hand, in this case to the right, and the force of friction acting against the can's motion. Since the can is moving in the direction that you are pushing, the force of friction and the applied force must be in opposite directions. We can write this as the summation of horizontal forces equals the applied force plus the force of friction in the opposite direction. And since the can is accelerating horizontally, these two forces cannot be equal in magnitude. This means the summation of horizontal forces cannot equal 0. And finally, since the can is accelerating in the direction of the applied force, we would draw the applied force to be greater in size than the force of friction. There's our free body diagram and a mathematical representation of the forces in both directions. You'll notice that each force on a single object is represented with a vector arrow and labeled to indicate the name of the force. For convenience, these vector arrows are drawn to point away from the object's center of mass. It is important, however, that we understand that these forces are actually acting on different parts of the can. Specifically, the gravitational force always acts at the center of the object's mass and can be drawn starting from the center of the can. The normal force and the frictional force are both caused by the surface, and so it must start from the bottom of the can where the table comes in contact with the can. Similarly, the applied force would begin where your hand makes contact with the can. Even though we simplify an object down to a dot that represents the object's center of mass, the center of mass being the average position of all particles in that object, we are cognizant of the fact that these forces are exerted at different locations on this three-dimensional object. Let's try a few more common examples. You kick a soccer ball into the air. Let's analyze the forces on the ball. Like before, there's the gravitational force acting on the ball at all times. There's the normal force from the ground supporting the ball, but only when the ball is on the ground. And then there's the applied force from your foot that kicks the ball into the air, but again, only when your foot is in contact with the ball. The types of forces acting on the ball are different at different instances of time. For that reason, we'll need to draw separate diagrams that represent the forces acting on the ball at a particular moment in time. So, before your foot touches the ball's at rest on the ground and would experience a downward force of gravity balanced by an upward normal force. The summation of vertical force vectors, the force of gravity plus the normal force in the opposite direction, and the horizontal force vectors would equal 0. The moment your foot makes contact with the ball still experiences the downward force of gravity, the upward normal force, and it would also experience the applied force. Since the ball is kicked into the air, we know that this applied force would be at an angle. At this moment, during the time in which your foot is applying this force, the ball would experience unbalanced forces and therefore accelerate. We can see this more clearly if we resolve the applied force into its vector components. If we were to total the vertical forces, the net force would be upwards, causing an upwards acceleration. We can write this as the summation of vertical forces equals the normal force plus the y component of the applied force plus the gravitational force in the opposite direction equals 0. If we were to total the horizontal forces, the net force would be to the left, causing a leftward acceleration. We can write this as the summation of horizontal forces equals the x component of the horizontal force, which cannot equal 0. Altogether, the net force is up and to the left, causing an acceleration up and to the left. After the kick, the ball is now moving through the air. The downwards gravitational force would still apply. However, since there's no other object touching the ball, this would be the only force acting on the object. Unless you consider air resistance, of course. Remember, air resistance is just a type of friction, so we can always draw the direction of this air resistance to be opposite to the direction of the object's instantaneous velocity. Let's say, at this moment, the ball is on its way upwards and to the left. This would mean that the force of air resistance would point exactly opposite to that direction, downwards and to the right. At the ball's peak height, we know it's only traveling horizontally to the left, and therefore, the air resistance would be directed horizontally to the right. Because the motion of the ball is changing as it travels through the air, so is the direction of the air resistance or frictional force. The free body diagram you draw not only represents the forces acting on an object and their relative sizes, but it represents them at a specific moment in time. Okay, let's not stop there. A husky tied to a sled by a rope pulls the sled, accelerating it across a patch of flat ice. Okay, let's analyze the horizontal and vertical motion of the sled separately. Let's start with the vertical direction. We've got the downward gravitational force, the upward normal force, and since the rope is applied at an upward angle, we've got an upward component to the force of tension. Vertically, the object's motion is constant, indicating balanced forces. This means if we were to calculate the net force, the sum of the forces vertically, the sum of the normal force, plus the y component of the tension, plus the gravitational force in the opposite direction would equal 0. Note that we're using the tension force and not the applied force, because even though the husky causes this force, the force is transmitted through the rope, and it's the rope that's in contact with the sled. In the horizontal direction, there's only one force, the horizontal component of the tension. You might think that since the sled is moving across the surface, that there would also be the force of friction. And technically, you are correct. But generally, when we're dealing with ice, the frictional force is so small, we tend to deem its effect as negligible. Horizontally, the object's accelerating, indicating unbalanced forces. This means if we were to calculate the net force, the summation of forces horizontally, it would be equal to the horizontal component of tension. Let's draw this out. We have the gravitational force downwards, the normal force upwards, and the tension force at an angle upwards to the right. When we draw this free body diagram, we must pay close attention to the magnitude of the vectors. The magnitude of the vertical vectors pointed upwards must total the magnitude of the vertical vectors pointed downwards in order for the sled to maintain constant vertical velocity. All right, last one. A girl on a skateboard coasts down a hill at constant velocity. Let's analyze the forces acting on the girl and the skateboard system. That means to say, let's consider the girl and the skateboard to be one object and analyze the forces acting upon them together. We'll start by identifying the forces at work. The gravitational force from Earth, the normal force from the surface of the hill, and the force of friction between the skateboard's wheels and the surface of the hill. Since the girl's skateboard system is moving at constant velocity, we know the forces in both the horizontal and vertical direction are balanced. Okay, let's draw it. The force of gravity acts downwards, as always. The normal force acts perpendicular to the surface, as always. However, in this case, the surface is at an angle, causing our normal force to also act at an angle. The force of friction is directed opposite to the direction of motion, so it will point up the hill parallel to the surface. All right. Now, how do we balance these vectors? We have two vectors that appear at an angle, so we can resolve them into their components and then balance their horizontal and vertical vectors. That means to say, we would make sure that the horizontal component of friction is equal and opposite to the length of the horizontal component of the normal force. And the vertical component of the frictional force plus the vertical component of the normal force combined are equal to and opposite to the gravitational force. Nice! That's definitely one way of doing it. This method, though completely appropriate, does require a lot of work. If we were to assign numerical values to these vectors, we'd have to solve for the components of the frictional force and the normal force. We can simplify this problem if we change our perspective. Currently, our perspective takes the y direction to be up and down, and the x direction to be left and right. What if we took this coordinate plane and rotated it so that the horizontal direction is now parallel to the inclined surface? Now, there's only one vector that is at an angle relative to this coordinate plane, the gravitational force. To ensure all vectors are balanced in this constant velocity problem, we'd only need to resolve our gravitational force into its components. We can do this mathematically through the use of our trigonometric functions of sine and cosine of the angle theta. This angle between the y component of gravity and the resultant gravity is equal to the angle of the incline. Therefore, the y component of the force of gravity is equal to the force of gravity times cosine of theta, and the x component of the force of gravity is equal to the force of gravity times sine of theta. In any case, along the x direction, the frictional force must balance the x component of the force of gravity, and along the y direction, the normal force must balance the y component of the force of gravity. Regardless of which perspective you take, a coordinate plane in which the x direction is horizontal, or a slanted coordinate plane in which the x direction is parallel to the surface, you must do so absolutely. That means you cannot take on two perspectives at the same time. Wonderful! We've now covered some common examples of constructing free body diagrams to visualize and represent the forces acting on an object. Though force vectors are drawn pointing away from an object's center of mass, it's still important to recognize where the force truly acts on a three-dimensional object. Additionally, it's important that the force vectors are drawn such that their relative sizes reflect their state of motion according to Newton's first law. To do so, we can separate the horizontal and the vertical motions, allowing us to analyze the horizontal and vertical force vectors separately. If either the horizontal or vertical acceleration is zero, for any object that remains at rest or in constant velocity motion, then the net or resultant force is zero in that direction. Likewise, if either the horizontal or the vertical acceleration is non-zero for any object that's accelerating, then the net force is non-zero in that direction. Finally, for any free body diagram, we may choose what x and y coordinate plane perspective to take, so long as we only take one perspective at a time. In our next video, we continue our study of forces with Newton's third law of motion. See you later on Penguin Physics.